Hello, and welcome back to Greg Does Physics. My name is Greg, and today we are going to be doing some physics. We are going to be doing problem 3.47 from Griffiths' Introduction to Electrodynamics. And 3.47 asks this. Show that the average field inside a sphere of radius r, due to all the charge within the sphere, is E average equals minus 1 over 4 pi epsilon naught p over r cubed, where p is the total dipole moment. There are several ways to prove this delightfully simple result. Here's one method. Part A. Show that the average field due to a single charge q at point r inside the sphere is the same as the field at r due to a uniformly charged sphere with rho equals minus q over 4/3 pi r cubed, namely 1 over 4 pi epsilon naught, 1 over 4/3 pi r cubed, integral q over script r squared, script r hat, d tau prime, where script r is the vector from r to d tau prime. So we can see that we have two setups here. One is we have a situation where we have some sphere of radius r, and we have our point with charge q at some position lowercase r within this sphere. And what we want to do is that we want to calculate the average electric field caused by this point charge q, that is the average electric field throughout this sphere. And then what we want to do is we want to show that that is the same as if we were to instead place a charge of minus q over the same sphere, uniformly distributed throughout that ball, and that's how we get this minus q over 4/3 pi r cubed, and calculate the electric field at that point, the same point where in this situation we place the point charge q, show that the electric field there caused from this configuration is the same. So if I start with the one situation on the right, what we can do is we can just write Coulomb's law, which comes from equation 2.8, I believe, and it's this: 1 over 4 pi epsilon naught integral of rho r prime over script r squared script r hat d tau prime. Okay. And so then this is equal to 1 over 4 pi epsilon naught. And then this is our rho here, minus, and since all of these are constants, we can just take it out of the integral. Minus q over 4/3 pi r cubed, integral script r hat over script r squared d tau prime. But you'll notice that in the equation for part A, it didn't have this negative here. And the reason for that is because the part A wants us to define this vector, script r, to be the vector from r being the location of our point charge q in the first configuration to d tau. So if we say d tau is over here, then our script r would be pointing in this direction. But in this case, we're calculating our electric field at the point r, and so the script r in here isn't the same as this script r. It would be pointing from the infinitesimal component of charge in the sphere, and it would be pointing from that infinitesimal charge toward our r, which is where we're calculating the electric field. And so we can see that in this case, our script r here is actually just the negative of the script r that the problem defines for us. Because if we take the negative of this script r, or the script r in this calculation, then it would give us the vector pointing from this location r to our element of volume d tau. And so with that in mind, we could just take out that negative. So there's that. And then over here, we want to compute the average electric field of this setup. And we could write that as the integral of our electric field at a given point over this volume, just over that volume. And so then our volume, of course, down here is going to be 1 over 4/3 pi r cubed, since it's just the volume of the sphere. And then our electric field we can write using Coulomb's law, except this time we're just going to use Coulomb's law in the case of a point charge rather than this one where it's a volume density. And so that would be 1 over 4 pi epsilon naught, which we can take out since it's constant, times q. So I'll just put the q over here. And then integral of script r hat over script r squared d tau prime. And this time our script r's are correct because our script r's are going to be pointing away from where we place the point charge q to whatever volume element that we're integrating at that moment. So 1 over 4 pi epsilon naught q over script r squared script r hat. And so we can see that these two equations are in fact the same. So yeah, that's all that part A asks us to do. Not too awful. All right, moving on to part B. So part B asks us this. It says, the latter can be found from Gauss's law. Express the answer in terms of the dipole moment of Q. So, before I go any further, let's write down the equation for the dipole moment Q, and that would be given by equation 3.100, which is this. And this is for a collection of point charges. And you'll see why I am writing the dipole moment for a collection of point charges in a second. Okay. So, it says the latter can be found from Gauss's law. The latter in this case is referring to calculating what this electric field is for the case where we have a spherical, a ball or a sphere, which has a total charge of negative q on it, evenly distributed throughout the sphere, and we could take our volume at a given radius within that sphere. So in this case, we want to find the electric field at this r, and so we could draw a Gaussian surface, which is probably kind of hard to see with all the different labels I have going on here. But imagine that we now have a Gaussian surface, which is just a sphere within this larger ball, and this sphere has a radius r. And so then we can use Gauss's law, which you should be familiar with. It looks like this. And we can bring our electric field term out of the integral for two reasons. One is because we can see that it should be collinear to our element of area over the surface of our Gaussian surface, this spherical shell that we've placed within the larger volume. They both should be pointing radially outward everywhere. And likewise, we expect that at a given radius, our electric field should be constant in its magnitude just based on the symmetry of the charge distribution. So then that's equal to this. But of course, our this is just the area of the Gaussian surface we picked, which is 4 pi r squared. And that's going to be equal to 1 over epsilon naught q enclosed. And so our q enclosed would be our charge density times the volume of this Gaussian surface. And so our charge density, so that's minus times minus q, 1 over 4/3 pi r cubed times 4/3 pi little r cubed. Because this is our volume charge density, and this is multiplying it by the volume of our Gaussian surface, which will give us the total charge that's enclosed by our Gaussian surface. Of course, the 4/3 and the pi's cancel out, and so what we're left with, also we can cancel out this r squared with this r cubed, and so what we see is that our electric field in this case is equal to 1 over 4 pi epsilon naught times minus q over r cubed r, and we expect it to point in the r hat direction, radially outward. 1 over 4 pi epsilon naught minus q over r cubed times r hat. Okay, so this is our electric field at points within this spherical ball of uniform charge density. Now, again, we've said that our, well, before I get to that, remember, so this is our electric field for this configuration, but we've said that our electric field for this charge distribution would be the same as this one, if rather than having a uniform volume charge density over the sphere of R and taking the electric field at a given position R, we could instead place a point charge that's equal to the opposite of the total charge over this sphere, and its electric field would be equal to the average over that. So we can say that this is just E average for our first case, where we just have a point charge Q, and we're looking at the average electric field over some sphere that encloses it. And our dipole moment, P, of this point charge Q would just be Q, and then times the location. This has a prime on it, but we're defining the location of our point charge as just R without the prime. So this would be our dipole moment for this point charge Q. And so we can see that R times R hat, well, this is the magnitude of a position vector times the direction of the position vector, and that is the same as just the position vector. So then our minus Q times the position vector here is our dipole moment. And so we can now write this as minus 1 over 4 pi epsilon naught, our dipole moment over the radius of the sphere cubed. And as we can see, equation 3.105, which is what we're looking for, is the same as what we've just found. So there we go. So and so using this fact that these two configurations are the same, then we can use Gauss's law to easily compute this electric field, and then we'll put it in terms of the dipole moment of our point charge Q and get this value. So we've shown what Griffiths wants us to. However, the problem does keep going, because point C asks us to use the superposition principle to generalize to an arbitrary charge distribution. I don't have to write anything this, I'll just explain it. If we wanted to find so let's say that we, rather than just having our point charge Q, we add a bunch of new point charges inside this sphere. Now, if we wanted to compute the average electric field over this sphere, what we could do is we could just compute the average electric field caused by each point charge and add them up. But likewise, in our calculation for the average electric field, which is given by this equation, our dipole moments, which are vectors, we could also just add up the dipole moment of every single point charge in the distribution that we've created. And so that would basically expand this to the point where we can confidently say that for any charge distribution we place inside here, the average electric field over that sphere will be equal to this equation where P is now the total dipole moment, i.e. the dipole moment of every single individual point charge added up. And we can create any charge distribution we want, it'll still hold up. And so that's how we would use the superposition principle to say that. Alright, and finally we get to part D, which asks us this. While you're at it, show that the average field over the volume of a sphere due to all the charges outside is the same as the field they produce at the center. And so we can imagine that rather than having our charge in the sphere, now what we're going to do is we're going to place it Q, and we'll still define this to be our position vector R, and we can still imagine taking some, our element of area, of volume, excuse me. So this equality will still hold up regardless of whether we put our point charge Q inside or outside of the sphere. This equality is still the same. So the idea should be that if we can calculate the electric field in an analogous situation where rather than having just a point charge Q outside of the sphere, we have a constant volume charge density like this over this sphere, such that the total charge is now negative Q, and we want to compute the electric field at this R, then that would be the same as our average electric field in the first scenario. So same idea as what we've done in part A and part B. And so again, we're going to use Gauss's law to do this, and we'll still have the same equation here, and so what we end up with is E. We can imagine putting our Gaussian surface now as a sphere outside here, outside of the sphere. So this side of the equation will still be the same, since this is integrating over the area of the Gaussian surface. But what's going to be different is our encharged close. Because before, we weren't grabbing this whole negative Q, we were just grabbing some fraction of it based on how far this original charge Q is placed, i.e. where our position vector is. But now what we're saying is that we have a net negative Q on the sphere, and now that our Gaussian surface is outside this ball, the encharged close is going to be all the total charge of this sphere, which again we've said to be negative Q. And so we can write that like that, negative Q. And so then that says that our electric field is 1 over 4 pi epsilon naught Q over R squared R hat. So according to what we found in part A, this being the electric field for our case where the charge is contained in the ball and we're calculating the electric field at this point, this electric field will be the same if the opposite charge is at that point and we're trying to find the average electric field over that ball. And of course, part D says that we want to show that the average field over the volume of the sphere due to all the charges outside is the same as the field they produce at the center. But what is the field that's being produced by this charge at the center, well, it would be given by Coulomb's law, 1 over 4 pi epsilon naught q over r squared r hat, where our separation vector would just become r, since our field point that which we're calculating is just the origin, except as we defined r here, it would actually be negative. The r hat would be reversed, since the script r would actually be pointing in this direction from the point charge toward the origin rather than away. And so we pick up the negative there. And so this shows us that the average electric field over this sphere is the same as just calculating the electric field from that point charge at the origin, at the center of that sphere. And that follows from being able to cleverly calculate the average electric field using our equality that we showed in part A, and then Gauss's law with this alternate charge distribution. That's what we said here. And then we can just compare that directly to what the electric field is with Coulomb's law from this point charge q at the origin. And we can see that these two things are the same. But part D asks us to while we're at it, show the average field or the volume of a sphere due to all the charges outside is the same as the field they produce at the center. We've shown this for one charge, 1 point charge, but we can generalize it to a collection of charges but just by invoking the principle of superposition. That is, we could put out any collection of charges we want outside of the sphere, and this equality, the fact that that the electric field, the average electric field over the sphere caused by that charge distribution, is the same as the electric field at the origin from that charge distribution, will still hold up just because of superposition. And so we can create any charge distribution we want outside of that sphere, and that equality will still hold up. So there we go. So yeah, this is it's a good problem. It gives us a little bit of interaction with the dipole moment, but doesn't tell us too much about the nature of the dipole moment itself. However, it is a very clever way to show us mathematically that these two situations are the exact same. And you can see that directly, you know. It's just that in one case, the 4/3 pi r cubed is coming from our charge distribution, evenly dividing this negative q up through it, whereas the other one, where we're calculating the average, it's that 4/3 pi r cubed comes from just taking the average electric field over that volume. The 1 over 4 pi epsilon naughts are the same, and then the only term left is the q's, which we say are the same, or opposites of each other, but the opposites are canceled out by the fact that whereas before this r was our source point and the element of volume was our field point, now we're saying that our field point is that r, and then our source point is each element of volume, and then we're adding that all up over the volume. And so that's where this negative comes out. But mathematically, we can see that they are the exact same. And that's really powerful. And we can see how the power of that makes this calculation of the average so much easier. Because in this specific case, or in this case, all we have to do is just use Gauss's law with a slightly different charge distribution, and then we can use that to make broader statements about the average electric field of a different charge distribution, just because we know that the equations are the same. So I do think this is a useful and cool problem for that reason. And that'll be all for this episode, so thank you for watching.